So my name's Laura Dalton, and I am a PhD candidate at North Carolina State University working with Dr. Porgaz. And today I will be talking about using X-ray CT to understand greenhouse gas and water migration in cement-based materials. So a little bit of background on why I'm interested in this research. So here on the right is an illustration of a well casing. There are millions of these throughout the United States, and they are constructed with steel as the production casing, and then cement-based materials are used to stabilize that annular casing. And so these are used to extract resources from deep geological formations, but then after the resource that we're trying to extract using these structures has been extracted, we sometimes use them for long-term storage of CO2. So we'll basically store CO2 down these wells, and then as a final barrier, we'll plug them with concrete. And so what I'm really interested in is the structure and service life and durability of these structures. So at this point, I am highlighting this little square up on the top right corner. So basically we're going to zoom in to the micro scale. And so that's what I'm showing here. So we've zoomed into the micro scale and we're looking at the entrained pore system of a cement-based material. And so here in red is CO2, so I've filled the voids with CO2 instead of air. In the middle, I've filled the voids with methane instead of air, and on the right, we have pure nitrogen filling the voids. Right, and I'm going to start this video, and basically what I want everyone to focus on is the transition to blue, which is representative of water. And I'm going to sit back and just let you guys watch this for a second. And so the main takeaway so far were these were observed for nearly an hour and a half at this point, and we're only seeing water advancement in the CO2 filled system. We haven't seen any water advancement in methane or nitrogen. And this is well into 2.5 hours. And then even by 6 hours, which is the next step, we're now seeing that the CO2 filled voids are now completely saturated with water, but nothing has happened in the methane or nitrogen filled voids. It's not until around 12 hours and even 24 hours that I see any changes in our entrained pore system when there's methane or nitrogen filling that void space. So from here, the question is, why is this happening? Okay, so here I'm showing degree of saturation on the y-axis and the square root of time on the x-axis. So this is a sorptivity plot in the case of cement-based material, where this is going to be a bilinear plot where there's an initial sorptivity and a secondary sorptivity. And so you have, why this happens is you have a dry piece of concrete, you put it in contact with water, initial sorptivity occurs as the capillary and gel pores, the capillary action takes over and those pores absorb water. And once that the smaller pore system is filled with water, only then do we start to see the larger entrained and larger capillary voids start to fill with water. So that's really what I was just showing on the previous slide, is the larger pore system becoming saturated with time. And so the difference here is in our above ground infrastructure, the air or the pore space is always filled with air, but in these below ground systems, there's the potential for them to become saturated with greenhouse gases. So that's really what I was showing, and that CO2 is filling much faster than methane or nitrogen. And so I was able to make these sorptivity plots using the CT data from 2 slides ago. And so that's the data points that are plotted for the secondary sorptivity region of this plot. And you can see CO2 filled much faster than methane, and methane a little bit faster than nitrogen. And so why is that? The solubility limit of these different gas phases in water are plotted here on the right. And so, and I have air just for reference. And basically what you can see is that nitrogen is lower than methane, and methane is lower than CO2. That CO2 has a much higher solubility limit in water. So it's able to dissolve in water faster. And that's basically what we were seeing and why we're seeing water absorbed at a faster rate in the pore system filled with CO2. But what's really interesting and was somewhat unexpected finding from this research is this nonlinear behavior that we were observing in the early portion of the secondary sorptivity region of the CO2 plot. So we started questioning, well, why is this happening? And what we believe it to be is a combination of a couple things. And so I'll explain that here on this slide. So here is a very simplified model of our pore system. So we have gel pore and a capillary pore, and they're tapered just to represent slightly different pore sizes, and they're connected to our larger entrained air void system. And it's lined with calcium hydroxide. And so what I did was purge the system with CO2 and then brought water in contact with these samples, and the initial sorption process took over. So water was absorbed into those smaller pores, but then what we believe was happening is that there was this transition point where a couple things are happening. So because CO2 can react with the calcium hydroxide present in the system, we're forming calcium carbonate. So it's a reactive absorption process that's happening. So that's one thing that is happening. Two, as the capillary forces are taking over, it actually, we believe, is reaching this transition point where the internal pressure within the larger voids is greater than that of the capillary forces. And therefore we reach this impasse where there's this transition from the outer saturated pore into the inner pore. And so that's happening and might explain that nonlinear behavior. And then secondary sorption occurs. So we're looking into this some more, but that was one takeaway from this research. But another bigger takeaway from this research is that CO2 is reactive, and that's what's was really interesting about this work. So the next question that really popped in my mind and that I wanted to research was, what happens immediately after cement-based material is exposed to an increased concentration of CO2? So what we just looked at was, we had a pore system with CO2, and we exposed it to water. Now I'm interested in, what if our pore system has varying amounts of water and we expose it to CO2? So kind of the opposite effect. But more specifically, what happens if we expose it to gas CO2, liquid CO2, and supercritical CO2? Because in the well environments, there's potential for CO2 to be in those different states. And so I did this using a micro-CT scanner at the US Department of Energy National Energy Technology Laboratory. And here on the outside of the CT scanner are ISCO pumps, which are used to just control fluid or gas flow into our pressure vessel that's housed inside the CT scanner. So I'm able to set the conditions I want to reach gas, liquid, or supercritical conditions in my samples that are dried to various moisture levels. And so then I'm able to expose them to CO2 immediately because of this valve at the very bottom of this setup. Basically, I turn it and it can expose CO2 and immediately see what's happening using micro-CT scanning over time. And so that combined with, I then also did thermogravimetric analysis, which can give me the amount of calcium hydroxide present in my samples after they've been exposed to CO2, and it can give me the calcium carbonate that was formed in these samples. So what I'm showing here on this plot is basically if I use the thermogravimetric analysis results combined with stoichiometry, I'm able to determine the amount of calcium carbonate produced from the calcium hydroxide that reacted. And so that's what I'm showing here in this plot. And here on the right, what I'm showing is that, so this is the remaining calcium carbonate that formed in the various samples that were tested. And so basically what this is showing is calcium hydroxide is only accounting for about 1/3 of the calcium carbonate that was produced in these various samples. And that clearly other phases present in the cement-based material is contributing to calcium carbonate formation. And so also looking at a little more detail using X-ray CT analysis, here we have a gas exposed sample on the left, in the middle a liquid CO2 exposed sample, and on the right a supercritical CO2 exposed sample. And so what you can see moving left to right is that the microstructure is changing, and that there's a large reduction specifically in the brightest material that you're seeing in the gas exposed sample. And so what that is unhydrated cement particles. And so that is reducing as we move from left to right, or from gas to the different CO2 states. And so using CT analysis, I was able to extract that volume and then convert it to a mass just using the density of the different materials. And that's what I'm plotting here on the bottom in the striped columns is the unhydrated cement after CO2 exposure in each of these samples. And then I've also plotted the calcium carbonate produced from other phases from the previous plot on the previous slide. And so this is just farther emphasizing that phases other than calcium hydroxide are contributing to carbonate formation under these various conditions. And then I also looked at slightly higher resolution scales. And another observation is that we're actually seeing calcium carbonate form under certain conditions in the very largest pore structure. And so here I'm showing in 3D, looking at that pore that's highlighted in red and how it's changing through the 3D space. So I'll show that again real quick. So the white portion here is calcium carbonate that formed in that pore space. And here is a 3D rendering of the calcium carbonate. So not only is the microstructure changing in our smaller pore system being affected by CO2 exposure, even the larger pore systems are showing indications of calcium carbonate under specific conditions, under specific moisture conditions. And so just a summary of what was just discussed. So basically looking at the effect of the gas phase residing in the pore space and how that affects transport. So a nonlinear response was observed during secondary sorptivity, specifically with CO2, and we believe that is due to this reactive absorption that's happening. The solubility of the gas phase influenced the rate of sorption, and so it's very important when it comes to mass transport. And this work was recently published in Transport and Porous Media if anyone's interested in more information on that. And then with respect to the second part of the talk, more focused on reactive transport of CO2, I'm finding that the degree of saturation and CO2 phase influence transport. It's very much a combined effect as opposed to just phase or amount of water present. And then phases other than calcium hydroxide are contributing to the carbonate that's forming. And lastly, just the carbonate is forming in a range of pore sizes. And that's very important moving forward. With that, I'd like to thank NC State and Nettle for all the help and support throughout this research. And I talked about a lot of heavy stuff, and just to take a moment for a little bit of nonsense. I don't know if anyone else has ever noticed that manatees look like floating potatoes. So with that, I thank you for your attention, and I'm happy to answer any questions.